So I'm going to press play here and see if this custom data that I encoded before plays back accordingly. And here's the message coming into the screen. All right, it worked. It took a few tries, but we got there. So in this video, we're going to make a Kansas City standard data encoder. So in the last video, I made the data decoder, and basically the data is computer or digital data is recorded in audio cassette format using a Kansas City standard, which uses 2.4 kilohertz and 1.2 kilohertz signals for high bits and low bits, and it's at a rate of 300 bits per second, and basically this uses UART communication protocol, which is 8 bits at a time with a start bit and some stop bits to store data. So today I'm going to show how to make an encoder. And when I did this last time, I used a test signal in order to test out the circuit. And I started by using a CD4106 clock at 2.4 kilohertz. And what I did with that was I put it through a D flip-flop as a toggle. And so that makes a 1.2 kilohertz divided by 2 clock signal. And I have those 2 clock signals being controlled by transistors and then put through a diode-based OR gate and then out through capacitors and a voltage divider in order to make an audio signal. The entire process is controlled by a CD4017 counter, which counts 8 clock cycles of the fast clock and basically a D flip-flop. The resultant timing diagram can be seen here, and as you can see after the OR gate, whatever the D flip-flop says at the Q output or the Q bar output is what comes out. And you get a signal kind of like this when you have alternating ones and zeros in the data. And it looks like a sine wave that's alternating with 8 cycles of fast and 4 cycles of slow clock speed. So when I use that for the encoder, for the decoder circuit as a testing signal, it worked very well to create this signal that I could use for testing. And so if this worked with the D flip-flop going high and low based on, the different bits, why can't I just put the data input through there, and then whenever the data is high, it puts out a fast clock signal. Whenever the data is low, puts out a slow clock signal. So let's test that out. To test this out, I'm going to use the data stream from the Star Trek game program that I recorded previously and used in my previous video. And I'm going to have that as the input to my encoder. I'm going to have the parent wave coming in on the yellow tracing of the encoder and from the tape player, and that's playing audio data. That data is getting decoded to actual UART data, and then that's getting re-encoded with our encoder circuit. And let's see how close the audio waves look. Let's go. And there it goes, high signal. All right. Let's stop it for a second and see how closely they match. They match pretty well. This is coming out of the cassette player. It's a little distorted here. And about the same peak-to-peak level. It's a little lower on the parent wave, a little higher on that. But that's pretty much it. And you see the lag behind. It lags behind 1, 2, 3, 4, 5 milliseconds. So here we go. Plug in any old data stream that you want, and it gets encoded into Kansas City Standard that could be saved on an audio tape. But let's take this concept a step further and see if we could generate our own data. So I got this FTDI cable, which basically allows serial communication between the whatever device you're using or building and a USB port on your computer. And we already have seen it in action with my decoder decoding this Star Trek game that I recorded from the cassette tape and displaying the data that you could see on the oscilloscope and on the screen. So now I'm going to press record on this cassette player and using the FTDI cable, punch in some random data, some sentence on the laptop, which will get transmitted to the encoder. And then from there, I'm going to have it encoded into Kansas City Standard. There's a simple sentence. And then I'm going to attempt to decode it and see what happens. And as you can see, this was a horrible failure. There's severe data corruption here, and the characters, some of them are coming through, but most of them are not. And the original sentence that I wrote is nothing like what is appearing on the screen. So this had me puzzled for a while until I tested it out on re-encoding the Star Trek basic program, the Star Trek game basic program in Kansas City Standard. When I re-encoded it, it worked beautifully when I played it from the cassette tape and transmitted the data through the FTDI cable into the laptop, and it read back beautifully without any real character or data corruption. So what is the problem? And this took me a while, but I finally figured it out. So the answer is synchronization. While the computer game data was precisely manufactured to be synchronized with the UART signal, when I was punching keys, they were randomly coming in at random points in the CD4017 count. And as you can see, the UART signal has a start bit. And if we synchronize the count from the start bit, when the start bit starts, it would provide the synchronization. So how to do this? So instead of my original design, which is here, I added two more components. A 555 timer in bistable mode, which would basically provide a synchronization start, and another counter that would count off the bits and stop the count when there's no data coming in. The way to use a 555 timer in bistable mode, you basically have to have pull-up resistors at the reset pin and at the trigger pin, and basically ground them when you're activating it. So the left-sided button is set and the right-sided button is reset, so it turns it on and off. And if I take the resultant signal and attach it to the clock inhibit of the counter, I can have that go on precisely when the start bit of the UART signal goes low and triggers the reset pin and activates the CD4017 counter. Finally, I put a second CD4017 counter in that counts to 10, basically 10 bits, goes over and over and over again, and it's activated by the reset output of the original CD4017 counter, and that counts 10 bits, and then it turns off the first CD4017 counter, resulting in this new revised timing diagram. As you can see from oscilloscope output here, you have the counts of the first CD4017 counter. It counts 10 times, and then it stops. And when the output of the bistable 555 timer goes high in between pulses, which you can see at the bottom of the screen. So to synchronize the data frame of the UART signal, basically I have this SR latch that gets triggered to go low and allows the counters to start counting every time the start bit starts. So let's see what that looks like when I play the tape. There we go. The lower signal is framing the UART, so you know where all of these are start and stop bits. Well, stop bits, because it goes up, it doesn't count during the stop bits, but it starts, it goes low and allows the counter to start counting when the start bit happens. So that's working just fine. If I stop it there, you can see start bit happens here, here, here on the falling edge, and when it falls, that gets triggered to go low, allowing the CD4017 counter to start counting the cycles, and that works. So now to test this, I have output going from the FTDI cable into the encoder, and it's being encoded into Kansas City Standard, and then that output is going to the decoder and being decoded, and then being fed back into the FTDI cable to be displayed on the screen of the laptop. And in the upper left corner, you could see the UART output at the top, and the synchronization signal from the bistable 555 timer at the bottom of the screen in blue. And you can see that there's no data corruption now that I've gotten rid of the asynchronization problem. So basically, the 555 timer in bistable mode functions as a controller for the CD4017 counter in the encoder circuit. And what happens is it stays idle in its high state until a start bit comes in from an incoming UART signal. So it doesn't matter how quickly or in what synchronized fashion I press the keys. It only starts counting bits at when that signal goes low, because the clock inhibit or clock enable is an active low in the CD4017 counter. And so here I am entering a whole sentence, and not one of the characters is corrupted. So in a second, I'll show the audio, or what the resultant encoded Kansas City Standard audio tracing looks like at the bottom of the screen. But here is the message I typed, and describes exactly what I'm doing. So here I'm doing basically more of the same thing, just typing in a message, and you can see the UART signal on the oscilloscope, the top left, and at the bottom you can see the resultant Kansas City Standard waveform that's being generated by the encoder. And it is only triggered by that start bit of the UART signal data coming in to the encoder. And as you can see, I'm going to zoom in on it in a second, but all of these characters are coming through unscathed. There's no corruption in the data whatsoever. So as you can see, as the UART signals keep coming in, the high bits and the low bits all have their corresponding high and low frequencies. And as I zoom in on it, the signal is spot on in terms of synchronization. So I think we're ready to retry the experiment with the tape. Let's do it. So now I have the encoder signal going into the cassette recorder, and pressing record, and it's time to start typing some data in randomly. I'm going to type in a whole long message, and I'm not going to show me typing here, but I will show the playback. The reason why you could see the text that I'm typing on the screen is because, in addition to the transmit line of the FTDI cable going out to the data input of the encoder, it's also going back to the data receive of the FTDI cable so that I can actually see on the monitor what I'm actually typing as opposed to typing blind. And so this is still me typing. I've sped it up as much as I could so you could see the entire message, so we can compare it to the playback message after I'm done with it and I play it back from the cassette tape. So here it goes. Let's press play and see the data coming out of the tape player, and it's basically being decoded now to see if we have any problems with the actual data. And as you can see, except for a glitch here and there with tape speed and motor problems, and some volume adjustments that needed to be made, it's pretty good. So that was the problem, the synchronization. As you can see on the oscilloscope, the audio signal from the tape is at the bottom of the screen, and the decoded data is at the top of the screen, and that's traveling in at 300 bits per second. So here is the final working version of the Kansas City Standard data encoder. And before I go, I'm going to play one more message for you in Kansas City Standard. So here goes.